Hello everyone. Now I want to discuss a very important rule called the octet rule. This is one of the bedrocks for chemistry. This is probably the most important rule for chemistry. But so far you should be very familiar with this periodic table now, and we have 18 groups. There's vertical columns, 7 series, 7 periods, and my apology, not series, 7 periods, and those are horizontal rows, and the 2 series. Then you have this what we call the S block, this what we will call the P block, D block, and F block. And remember, initially Mendeleev organized the modern periodic table based on similarity in chemical properties. That's how those groups are actually organized based on. And later on, with the development of the atomic structure, understanding of the atomic structure, subatomic particles, and subsequently answering that essential question: are those electrons surrounding the nucleus organized? We'll arrived at the Schrodinger's model. And after all these exercises, we now realize the the organization of the electrons are quite matching very well with the chemical properties. As we see it, for the group 1 elements, the valence shell electron configuration will be generalized as NS1. It's always end up on the outermost S sublevel with 1 electrons. And the Lewis structure with just a single dot. And now the group 2, S2, group 13, 14, 15, 16, and 17, and 18. All this, one thing you have to mention again is for group 18, there is an exception. That will be the helium. Helium only have 2 valence electrons. And for the rest of the elements in group 18, they all have 8. They all have 8 4 pairs. They all have 8 4 pairs. So now we start actually arriving at the important conclusion is the valence electrons is the determining factor for the chemical properties. As we say, they are similar in chemical properties and they are exactly the same in terms of valence electron configuration, but it's on different principal energy levels. So as we focusing on the different groups in the series, one thing jump out of it. You learned it since your elementary school days, is the fact that the group 18 are called noble gases. Those are called noble gases. Why do they call it noble gases? Not actually common man's gases. The reason why is, if you understand the noble people, they do not want to mingle with the common folks. So element in the group 18, they rarely react with any other elements on this periodic table. Except, the exceptions for xenon. Xenon react with fluorine. And that's about it. And why they don't want to react with anybody? They're happy by themselves. So they don't need anybody. They don't need to form any bonds. In essence, so there will be the key conclusion. Then the valence shell electron configuration for the noble gases are the most stable one. Hence, all the other elements on this periodic table will have ground state electron configuration, valence shell electron configuration less stable than those noble gas electron configurations. And when those are not stable, unstable ones, what do they want to do? They want to get to the stable state. And here comes a very important observation. Let's bring out a pen. I would like to use the red color. So it's about 2 observations. Okay, the first observation is noble gases have the most Okay, after resolving some technical difficulty, let's continue the discussion. So we have two key observations, and the first one is all noble gases have the most stable electron configurations. Among all the elements. On a periodic table. And the second one is all other elements want to achieve noble gas electron configuration. This is a very powerful couple of points, and this is called octet. The reason it's called octet because for all the noble gas elements, they all have this 8 valence electrons. Keep in mind, helium has 2. So then the exception will be helium. Helium will have 2. 2 also very stable if you only have a single ring. So this, as I said before, will be the bedrock of chemistry. Why is that? So let's take a look at some examples. Let's take a look at sodium. Sodium atom, you know sodium atom is less stable than noble gases. So what will the sodium atom do to get to the more stable electron configurations? So then it has to go with the circular plot. Let's take a look at the circular plot for sodium atom. So we have plus 11, and we should have 3 rings. And now let's change in the color. How many electrons should I have? First ring will have 2. 1, 2. Second ring we should have 8. 1, 2, 3, 4, 5, 6, 7, 8. And the last ring I should have just 1. 3 of 1. Okay, so what would it do to achieve the noble gas electron configuration? What will happen? There are two ways. Okay, either you gain 7 electrons, or this alternative. If you can clearly show here, very interestingly, you will notice there are about 80 electrons underneath. If I can erase this, the outermost shell, then you can have 8 electrons. So then you gain 7 electrons, so you lose 1 electron. So conceivably, which one will be easier? And by losing 1 electron will be much easier. However, by doing that, the sodium is not charge neutral anymore because you only have 10 electrons here, but you have 11 protons inside. So in a sense, the sodium, by losing 1 electron, is going to become sodium ions. And now it achieved the noble gas electron configuration. It is stable.
That is actually the reason why for all the group 1 elements, they will turn into +1 charge ions. +1 charge ions. Take a look at the second example. What happened to chlorine atom? And we said, let's take a look at the superplot. Superplot will be +17, and we're going to have 3 rings again, as we can deduce that from the ground state electron configuration. So then it takes a little while to draw it, but I'll draw it. So then you have one here. Oh, I gotta fix this problem. Not a very good drawing. Okay, let's draw the last ring. Much better. And number of electrons should have 8 on the second. 1, 2, 3, 4, 5, 6, 7, 8. And on the outermost, the valence shell, we have 7. 1, 2, 3, 4, 5, 6, 7. Also facing 2 choices. Either you gain 1 electron, or you're going to lose 7 electrons. So which one is easier? And this one, gaining 1 electron. On paper and both energetically will be much easier. So in this case, and this chlorine will be gaining an electron, becomes a chloride ion. It'd be interesting you actually take a look at it now. The names now is sodium is called sodium ion, and this is what's going to be called chloride ion. We call it chloride ion. You can continue this exercise, and you will see a lot of calcium will turn into calcium 2 plus. Take a look at the circular plot, and also you notice when you lose electrons turns into positive charge, the cations, we use the same name as the element name. Okay, same name as the element name. Now if there's oxygen, take a look at the one, you're going to gain 2 electrons, and it will be 2 minus, and now we actually call them oxide. Okay, so now start looking at, there's some naming convention here. For losing electron, same name as the element. For gaining an electron, we're going to change them into ending with IDE. Okay, as we said it before, then fluorine is going to turn into fluoride, chlorine to chloride, chlorine into chloride, and bromine into bromide, iodine into iodide, and iodine into iodide, oxygen into oxide, sulfur into sulfide, and nitrogen into nitride. And the list goes on and on and on. And then you can ask, what would be the consequence of actually we're putting our sodium and chlorine atom, in this case is diatomic elements. Don't forget there are about 8 of them. Remember we covered that in the previous unit. If we plus this 2, what will happen? Naturally you will say, oh, this one's going to lose electron, and this one's going to gain electron. In this case, one of them is going to gain each electron. Both of them will be happier to achieve noble gas electron configuration, and this one in this case is sodium ion and a chloride ion. Sodium ion and chloride ion. And here's what I want to show you, the results of putting those two together.
A small piece of sodium metal is placed in a flask containing yellow chlorine gas. The flask also contains sand to prevent the heat which will be generated by the reaction from cracking the glass. Initially, no reaction is observed between the sodium and the chlorine. The reaction will be initiated by adding a drop of water to the sodium.
As everybody can see from that demo video, and this is what is driving the excuse me, this is what driving the chemical reaction. Because all the elements have that strong desire to achieve noble gas electron configurations. In this case, a lot of them want to go to have 8. Thank you very much for your attention.